This tutorial is the first of three that will illustrate the various forms of DC analysis with Multisim. For all three of the tutorials, a very simple circuit will be used. The intent is to show how a simple circuit that can be analyzed by hand and readily predicted as far as the results are concerned can be correlated with the very sophisticated approaches taken in Multisim. Now this little circuit here is a voltage divider type of circuit. We have an 18-volt DC source, and by the way, the ideal DC source is called DC power in the power sources bin. We have two resistors, 6 ohm and 3 ohms, and there must be one ground node in any circuit, and the ground node will always assume the value 0. Now one can readily see that if you look at the resistance seen by this source, you have 6 ohms plus 3 ohms, or 9 ohms, divided into 18 volts gives you 2 amps clockwise, and you would wind up with 12 volts across here, 2 times 6 by Ohm's law, and 2 times 3 or 6 volts across this resistor. So let's use the power of Multisim to achieve the same result. And notice I've labeled this node as in, this node is out, and the source has been named V source. Now there are two ways to do the analysis that I'm going to do next. This particular analysis in this tutorial will involve the DC operating point analysis. That particular name comes about because of the original primary mission of the program, the SPICE program, when it was first developed many years ago. There was a DC analysis to determine DC variables in the circuit, and then an AC analysis, and since many active devices would be biased at a particular operating point, hence the name DC operating point. Now there are two ways to initiate this analysis. One way is to go up here to simulate, click, and then come down to analysis, and you notice that this thing opens up here, and you can choose among many different types of analysis, of which DC operating point is at the top. That's okay if one wants to use that. I personally prefer to utilize a different type that you save one step. If you'll notice along here, there's a little bar, a little icon called a grapher. It's right next to this particular one here, which is fairly visible when you look at this entire area here. So I'm going to click on grapher, and you get the same menu that I got with two steps over on the left hand side. So I'm going to hit the DC operating point. So I hit the DC operating point, and this opens. Now I'd like to show you first the way it would come out if you've just built the circuit. It turns out that when you leave variables set up for viewing, some of them remain in the active area. So what I'm going to do first is come over here where you see I of R1, and I'm going to remove it. Now this is the way it comes up when you first set the circuit up. There are no variables on the right hand side. All the possible variables are on the left hand side, and here are the way they are designated. You have I of R1, meaning the current in R1, I of R2, you have I in the voltage source, and of course all three of those are the same in this circuit. You see, you get a large number of variables even with a simple circuit. Then we have the power in R1, the power in R2, the power associated with the source, Vin and Vout, the two node voltages with respect to ground. Now I'm going to add all of those over on the right hand side so we get a listing of every variable in the circuit. Now you can do it one by one. That one's been highlighted. I can put it in. I can then add this one, or I can hold down the control button on the keyboard and highlight all of them and add them all at the same time. As a matter of fact, you can add certain kinds of mathematical expressions by simply clicking on this one here, add expression. Now, we've just about got everything in the circuit covered, but one that's not been covered is V of R1. But what we will do is write an expression to illustrate how you can do an algebraic expression. I'll put V of N, that's the voltage on the input node, minus V out. And I'll OK that so it shows up also. It showed up not at the bottom, but here, Vn minus V out. Now I'll hit simulate. And we have a screen now appearing in which all the variables that I indicated are shown. If that shows up, sometimes that will show up minimized, just maximize it if necessary. Some of these numbers may be hard to see for someone viewing this, so I will make sure that I read them all. You also have the option of having this dark background, or you can go up here to graph, click on it, and toggle to white colors. I'm going to go back to the black color again, and I will read these quantities, and certainly if you see the circuit in front of you that you might have drawn on a piece of paper, you can readily verify all of these. A lot of these are the very same thing. For example, I of R1 and I of R2 and I source basically are all the same. However, notice that I of R1 and I of R2 show up as 2 amps, but I of V source shows up as minus 2. Now, the reason for that is that for a source, a positive value of current is indicated as current flowing into the source. Now, since we only have one source in this circuit, it obviously must be supplying current to the rest of the circuit. So the positive direction of current flow is out of the source, and therefore it shows up as minus 2 rather than plus 2. Now, looking at some other variables in the circuit, Vn is 18 volts. That's the same as the source voltage, of course. Vn minus V out, well, V out is 6 volts because we get 1/3. If you go back and look at the circuit, you see the voltage division is 1/3 between the source and the output. So you get 6 volts on the output. So the voltage across R1 is 12 volts, and Vn minus V of out came out as 12 volts. Now, for the power values in the circuit, we have P of R1. Now, I was 2, so I squared times R is 4 times 6, which is 24 watts. Now, P of R2 would be I squared times that resistance, so that's 4 times 3, which is 12, or you could take V times I. That certainly will give you the same result. There is something strange here, though, that you need to consider, and that is that P of source is listed as minus 36. And the reason is that the convention of power is that power being delivered is negative and power absorbed is positive. So that minus 36 watts means it's really plus 36 watts delivered, or minus 36 watts absorbed. And the power delivered must equal the power absorbed within the circuit. So if you add 24 and 12, you get the 36 watts absorbed within the circuit. So that takes care of this particular operation. Let me minimize that. I think we pretty well calculated just about everything within the circuit, but just to correlate this again, I'm going to close out on that one. We have 18 volts causing a positive conventional current flow of 2 amps flowing into the 6 plus 3 or 9 ohms. So we have 2 amps. We have the 2 squared times 6 or 24 watts here, and 2 squared times 3 or 12 watts here. I think I've pretty well covered just about every variable that we can have within this simple circuit. Now, subsequent modules will take this very same simple circuit and illustrate some other operations that can be done with Multisim.